All right, so recall in the statement of Green's theorem that the region that's enclosed by our curve C has to be simply connected. So what if I have a non-simply connected region? Say this region right here, this annulus, I'll call it R, and the boundary of this region is this outer circle in blue together with its inner circle in blue. And it's typical to refer to the boundary of a region using this del R notation. Okay, now del is the same del as in partial derivatives. Okay, so del R here is denoting the boundary, which is just these two circles. Since this is not simply connected because of this hole right here, Green's theorem does not apply directly. Okay, but nonetheless, is there something I can say with regards to the results of Green's theorem in connection to this region? Well, there is, but we have to be a little bit tricky. Okay, so I'm going to create a little cut in this region along this little line segment on the positive x-axis. And I'm going to pull this region apart a little bit. Okay, so this is going to give rise to this new region I'll call R prime, shaded in white. And I'll call the boundary of R prime, which is this blue curve here, and then we go along this edge, and then we traverse this inner portion here, and then this edge here. That all together, I'll denote by del R prime. So that's the boundary of this new region R prime. This thing is simply connected. When you pull these two edges apart like that, you lose the whole. Okay, so Green's theorem does apply to this region R prime, and so I can say that the line integral along the boundary is equal to this double integral over the region R prime of this quantity partial q partial x minus partial p partial y. Now notice the orientation here for the boundary of R prime. So for this outer piece, I'm walking in a counterclockwise fashion. But then when I get to this edge, I'm going to turn in here, and then I'm going to walk along this inner portion of the boundary. And notice here I'm walking in a clockwise fashion, okay? And then I'm going to follow this out right here to close out the region, all right? So again, Green's theorem does apply to this modified region. So the idea now is to paste these back together. And so more formally, you'd want to take a type of limit here, but by putting them back together, we're going to return back to this original region R. And the question is, what's going to happen to these resulting integrals when you paste back together? Well, what's going to happen is that the contributions along this edge where you're piecing these two back together are going to cancel out because their orientations are reversed, okay? They're opposites of one another. So those will actually cancel out. And what this result here for this modified region will result to for our original region R is that the line integral of our vector field F over the boundary, so over this outer blue circle and then combined with this inner blue circle, that will equal the double integral over the region R of this same quantity, partial q partial x minus partial p partial y. Okay, I'll refer to this as the modified version of Green's theorem. Okay, now also notice the orientation for the boundary. Okay, so uh, I'm walking counterclockwise along this outer circle, but then for this inner circle, okay, I'm actually walking clockwise, and that's because this region here is picking up its orientation, right, from all of these regions here that we're having to orient just based on the counterclockwise convention for the initial Green's theorem that we applied at the beginning of the section. Okay, so I think actually, in all honesty, a better way to describe the orientation is not in terms of counterclockwise and clockwise like our textbook insists to do so. I think it's better to say, hey, as I walk along any portion of my boundary, then the region R is always off to my left. Okay, so if I'm on this inner piece here, notice that if I want the region to be off to my left, I'm actually going to have to walk clockwise along that portion as opposed to counterclockwise. All right, so now what if I had a more general region, like say something like this? Well, by a very similar argument, okay, we can still get a modified version of Green's theorem to follow. Okay, so if I call this region R, and right, it's not simply connected because of these holes, but I'm going to have this positive orientation where on this outer boundary piece, I am moving counterclockwise, but now on these inner boundary pieces, notice I'm walking clockwise, and that's because I always want my region R to be off to my left as I move along the boundary. Okay, and now with that orientation, we still get that the line integral of our vector field over the boundary, where again I have to pay attention to orientation, is equal to the double integral of this quantity partial q partial x minus partial p partial y over the region R. Okay, so in the next video, we're going to look at question 4, which is a really, really good illustration of all of these ideas. And we'll tie a number of things together for us, and I will see you there. All right, thanks.